Okay, so let me share my screen. So my thesis is about representations of symmetric groups of Chow rings of Boolean matroids and extensions. So let's first talk about what it's a matroid. I won't give a like a strict definition. So just give an example from linear algebra to kind of let you know how to think about it. A matroid, so a matroid M on the ground set 1 through n set of rank R, you can think of it as an abstraction of vectors V1 through Vn that span an R-dimensional vector space. So for example, the column vectors of these matrix, V1 to V4, these forms a matroid on 1, 2, 3, 4, on 1, 2, 3, 4 set of rank 3. And when we have a matroid like this, we can talk about an independent set of a matroid. And in this case, you can think of it as just all the linearly independent subsets of these 4 vectors. And in this case, well, we will just record their corresponding labels. So in this case, the collection of the all independent sets are these things. You have empty set, all the singleton, and then all the 2 subset. And we also have 1, 2, 3. These is an independent set, 1, 2, 4, and so on. And now here only 2, 2, 3, 4 is not an independent set because they are linearly dependent. And we can also talk about the rank of a matroid. For example, well, the rank of these, so rank of a set, for example, rank of 1, 2, 3, so it's V1, V2, V3, this span a dimensional 3 subspace. So we just say its rank is 3. And rank 2, 3, 4, it spans a dimension 2 subspace, so rank 2, 3, 4 is 2. And we can also talk about the flats of a matroid. This just means you can think of it as all the subspaces spanned by the subset of V1, V2, V3, V4. And for each of these subspace, each of these subspaces is represented by the maximal subset of the vectors they span it. So for example, we can see if we just look at 2 and 3, this is not a flat because the space spanned by V2 and V3, you can see that V4 is also in this subspace. So 2, 3 is not a flat, but 2, 3, 4 is a flat. Yeah. And if we collect all these flats of these matroids and consider their inclusion relation, containment relation, then you can form a partially ordered set graded by the rank, which we call the lattice of flats of the matroid. And on the left-hand side, this is the Hex diagram of this post set. And well, when we have a post set like this, we usually, if you have a unique maximum element, we usually denote it as 1 hat. And when it has a minimal element, the convention is we denote it as 0 hat. Okay. And okay, and in our thesis, we also mentioned this is Boolean matroid, which is very special for us. And you can just think of it as the collection. This is just an n linearly independent vectors. And so any subset of these vectors itself forms a subspace and they are all distinct. And so the lattice of flat of the Boolean matroid, this is just the subset, all the subset of 1 through n sets with the containment relation. And so this is just the Boolean lattice, and that's why we call this Boolean matroid. And now with have a matroid, we can associate it with an algebra called the Chow ring of a matroid. And it was first introduced by Fechner in Zvinsky in a more general setting. So first, if we have a geometric lattice, or you can think of it as the lattice of flat of a matroid, and there is some certain subset of L satisfy some special condition called the building set. If we have a pair like these, a L and a building set, then we can associate it with a simplicial complex, this N tilde LG called the reduced nested set complex. And for the combinatorics people, the special case is if the building set is these L remove the minimal elements, this is also the maximal building set, then the simplicial complex is exactly the order complex of the proper part of L. And so Fechner and Zvinsky, they use this construction to introduce these algebra, DLG. This is called the Chow ring of L with respect to the building set G, as some quotient of the Stanley-Reisner ring of the reduced nested set complex. And it turns out, so these quotients will be finite dimensional Q algebra, and they also obtain the basis for this algebra. So Adiprosito and Katz in 2018, so in their paper to prove the long-standing Rota-Heron-Welch conjecture, they consider this DLG in the case that L is the lattice of flat of a matroid and G is the maximal building set. And the ring, this ring now is now referred to as the Chow ring of a matroid. We usually denote it as A of M. And if you want to know the explicit expression, this is the expression of A of N. So on the numerator part, this is actually a Stanley-Reisner ring of the reduced nested set complex. In this case, is the order complex of lattice of flat of your matroid. Yeah, and it has, and in this case, the Fy basis, it has a basis, what you denote as Fym, it looks like this. So at this moment, we don't need to really remember what this expression look like. Okay, so later, Brandon Hermith and Pravud and Wang, they in 2020, so they tried to prove another long-standing Darwin-Wilson top-heavy conjecture. They introduced the augmented Chow ring of a matroid as an extension of the Chow ring, which has the explicit expressions like this. So you can see, as compared with the Chow ring case, it has an extra variables, this y1 to yn. Yeah. And later we will see that the numerator part is also a Stanley-Reisner ring of some other simplicial complex. And so the Chow ring and the augmented Chow ring of matroid is the main character in our thesis. So next, well, we will use the theory from Chow ring to try to study the Permitohedral varieties. So what is the Permitohedral variety? It is a toric variety associated to the normal fan of a polytope called the permitohedron. And so permitohedron, you can think of it as a convex whole of all the permutations of length n. So zero lambda is the coordinate inside Rn. And so on the right-hand side, you can see this is an example when n equal to 3. The hexagon is the permitohedron. And in this case, the normal fan is just the fan generated by these 3 of reflecting hyperplanes. And an intriguing fact about this permitohedral variety is that its concurrent polynomial is the classical Eulerian polynomial, which we denoted as an of t, which can be defined as counting the statistic number of exceedance over the permutations. And so we can let a symmetric group acting on this normal fan by just permuting the coordinates, and this will induce a representation of Sn Arnical homology. And so now if we let this CH, this is a map sending a representation of symmetric group to the ring of symmetric functions. This is called the Frobenius characteristic map. And we can use this map to encode the representation of symmetric group as a series of symmetric function or polynomial and symmetric functions, usually called the Frobenius series. So Stanley in 1989, he used a recurrence relation from Procesi to compute the Frobenius characteristic of Frobenius series of these cohomology and obtain the following formula, where this h of z is the generating function for the complete homogeneous symmetric function, this Hn. And from here, this implies that the cohomology is actually a graded permutation representation. And on the other hand, so Stanbridge in 1992, he defines combinatorial object called code. And this is just a sequence alpha over non-negative integers, such that if you have if this m of alpha is the maximum number appearing in the sequence alpha, then for each of the number between 1 to m alpha, this number will occur at least twice in the sequence. And there is a mark assigned to one of the occurrence of this number after its first occurrence. So this is an example of a code. You have a sequence, and m alpha here is just 3 because it's the largest number. And you can see that 1, 2, 3, they both has at least twice occurrence in the sequence. And we have this mark assigned to each of the 1, 2, 3 that satisfy the condition. And we usually denote a code in the pair alpha f, where alpha is a sequence, and f is defined as, so f of j by this. So f of j is just the number of j's in front of the mark j. Yeah, so in our example, alpha is this thing. And we can see now, so in front of the marked one, there is 2, 1. So f of 1 is 2. And in front of the marked 2, right here, you have 1, 2. So f of 2 is 1. And similarly, f of 3 is 1. And with this, we can define what is called the index of a code. And this is just the index of this code is just the sum of all the f value. So in our example, the index is just 2 plus 1 plus 1 is 4. So we have a code and we have an index. And these are just codes of length 3. We have 6 of them. And the index, corresponding index form the distribution 1, 4, and 1. Oh, okay. Now if we let this code nj be the set of codes of length n with index j, then we have a symmetric group acting on codes by just permuting the sequence part and let the f value unchanged. And this will make our linear span of code as permutation representation of Sn. So Stanbridge in 1992, he computed the Frobenius characteristic, Frobenius series of these representation, and show that it has the same formula. So it's actually isomorphic to the cohomology of the permutohedral variety. And he then proposed a problem of finding a permutation basis for the cohomology of permutohedral variety that induced this representation. And in our work, we will give an explicit permutation basis in terms of the Chow ring of the permutohedral variety, and we will relate it to Stanbridge's codes. Okay, so first we will identify cohomologous Chow ring using this theorem by Danilov and Stanbridge. So it says that if P, we have a polytope P, this is an n-dimensional simple lattice polytope in the n-Euclidean space. And if a finite group Gx on the normal fence simplicially and freely, then this cohomology of this toric variety associated to the normal fan of this P is isomorphic to the Stanley-Reisner ring of the boundary of dual P, and then you're modding out some linear form, which is defined as the following. And they're isomorphic as this G module when we have this G action. Yeah, and the right-hand side, this thing, we usually denote it as A X sigma P. This is known as the Chow ring of this toric variety X sigma P. So with this theorem, now we consider our matroid to be the Boolean matroid. In this case, the lattice of flat is the Boolean lattice. And it turns out the reduced nested set complex for this Chow ring is exactly the boundary of a dual permutohedron. And one can show that the Chow-ring of Boolean matrix is exactly the Chow-ring of the permutohedral variety. And so by Danilov and Stanford's theorem, they are isomorphic as a module. And in this case, because this is Fashionov-Svinsky's Chow-ring, we have a basis, which turns out have expression like these. So these are has the monomial base. These are monomials indexed by chance inside the Boolean lattice. So they're all subset of 1 through n sets with some conditions on these AI. So for example, this is a basis element. The chain is like this, n equal to 8. And now, and it turns out this will be a permutation basis they want. And then we have a permutation basis, and we further constructed as an equivariant bijection between this basis and the codes. And this bijection sends the degree of the monomial to the index of the codes. And the bijection, well, we can just see an example. This works as the following. So this is an element of basis, and these corresponding to a code as a following way. So we look at the first set, this is 1, 3. So we put 1 in the first and the third positions. And then degree is 1, exponent is 1, so we put a mark here. So f of 1 is 1. And then we add, in the second set, we add 2 and 5. So we add 2 in the second and fifth positions. Exponent is 1. So we have marked here. So the f of 2 is still 1. And the third, we add 4, 6, and 8. So we add 3 in fourth, sixth, and eighth positions. And the exponent now is 2. So we put a mark here so that f of 3 is 2. And after we go through all the sets, if there is still empty space, we just put 0. And if this forms a code. Yeah. And that's the bijection works. So it's have these bases has basically the same structure, combinatorial structure as the Stanford's codes. Okay, and when n equal to 3, this is how the bases and the codes, they correspond to each other. Yeah. So next, we proceed to see a kind of parallel story, starting by what we call the binomial Lagrange polynomial, a n tilde of t, defined this way. And Postnikov, Reiner, and Williams in 2008, they showed that these binomial Lagrange polynomial is actually the Poincare polynomial of some toric variety associated with the normal fan of a polytope called stellohedron. And this we denote as a pi n tilde. On the right-hand side, this is an example when n equal to 3. You can see in the middle, there's a facet, just the hexagon, the permutohedron. So this is some kind of extension of the permutohedron. And Suresh and Wax in 2020, they introduced these symmetric function analog of the binomial Lagrange polynomial this way, where this pk is just the Brady-Fabin series of a cohomology of permutohedral variety when n equal to k. And they further showed that the Fabin series of the stellohedral variety cohomologous stellohedral variety is exactly the symmetric function q n tilde xt. So and we can just see by the definition of these things that these cohomology carries a permutation representation of Sn. And now similarly, so we then define this thing called the extended codes, and this is just a code alpha f, where alpha is still sequenced over non-negative integers, but now besides the negative integers, you will have some infinity inside that's just working as just as the zeros in the Stanford code. So there's basically no restriction on infinities. And the index of an extended code is still defined as before for the code. So infinity doesn't affect. And except that when we define the index of the O infinity code to be -1. So yeah, this is an example. This index is just still the sum of these f values, so infinity doesn't affect. Yeah. And now we let code tilde nj denote the set of extended code with of length n with index j. Then so these are the examples of the extended codes when n equal to 3. We separate them according to their index from -1 to 2. So we will have 1, 6, 6, 1. These many extended codes. And similarly, we have essence representation carried by these linear span of extended codes. We compute the Frobenius characteristic of these representation and show that it's exactly the same as these Q and tilde xt. So it's the representation we want. So it is isomorphic to the cohomology of the stellar variety. And now we can ask the same question. So can we find the permutation basis for the cohomology of the stellar variety that have a similar combinatorial structure as the extended codes? Yeah. And it turns out that yes, we can find the basis, but it's way harder than the permutohedral case. So we consider these augmented Chow ring of a matroid, and it has a geometric counterpart called the augmented Bergman complex or Bergman-Fan complex. And the theorem of Brendan, Hermith, and Proudfoot and Wang say that the augmented Bergman-Fan of the Boolean matroid is the normal fan of the stellarhedron, and the augmented Bergman complex is exactly the boundary of the dual stellarhedron. And that's why we start consider these augmented Chow ring. And one can show that this augmented Chow ring of Boolean matroid is the same as the Chow ring of the stellarhedral variety. And so they are, by Danilov-Stanbridge theorem, they are isomorphic as a Sn module. But the different part is that when we're doing this project, there's not many things known about this augmented Chow ring. Also, there's no basis in our known. So we need to find a basis, and it turns out that we finally find a basis which is analogous to the Fechner-Zvinsky basis for the Chow ring. And when M is Boolean matroid, this basis has expression like this. It's very similar to the Chow ring basis, just the first expression, the first set, its exponent is a little bit different. And when n equal to 3, these are the basis elements. You can see you have 1, 6, 6, 1. And yeah. And these bases turns out will also form a permutation basis. You can see they are invariant under the Sn action. And also we construct an Sn equivariant bijection between these Fechners, between these bases and the extended codes, and it sends the degree of the monomial of basis -1 to the index of extended codes. Yeah. And well, the bijection is kind of similar. But you break it into two cases according to the first exponents of the first term. The first term is exponent. If the exponent is 1, then when you plug in numbers, you're starting with 0, 1, 2, and so on. And when you go through all the subset, and you still have empty space, then you just put infinity in. And in the second case, if your first term is exponent is greater than 1, so here's 2, then you just starting putting number from 1, 2, and so on. So not 0 is 1 instead. So 1, 2, and then similarly, if after you go through all the sets, you still have empty space, then you just put infinity. And then you can get this bijection of the basis and the extended codes. Okay. So now how do we obtain the basis? So basically, we have seen that the Chow ring of a matroid is a special case of this DLG with L is the lattice of flat of matroid and G is the maximal building set. And we saw this Brendan, Hermith, and Proudfoot and Wang. They introduced the augmented Chow ring and the augmented Bergman complex when M is Boolean. the augmented Bergman complex is the boundary of a dual stellohedron. And on the other hand, Postnikov, Reiner, and Williams in 2008, they consider L to be the Boolean lattice, Bn plus 1, and then some building set called the graphical building set of an N-star graph. And in this case, the reduced nested set complex is also the boundary of the dual stellohedron. And so in this case, we actually have two different ways to construct the dual stellohedron. And you can see there's also some empty, like a blank here. So what we did is we compare these two different ways, and then we also try to fill out these blank. And when we do that, it turns out that we got the basis directly. Okay, so now let's first start with the augmented Bergman fan of a matroid. So M is a matroid on ground set N, 1 through N. That is of flat Lm, and we have this independent complex of In. Then the augmented Bergman fan is just a simplicial fan whose cones are indexed by a pair of independent set I and a chain inside a lattice of flats of your matroid F. Oh, and the chain does not contain the largest element 1 through N set. And we request these two I and this F need to satisfy these I's contain the minimal element inside your chain. Yeah. And so we call this the compatible pair I and F. So our cone is indexed by this compatible pair. And if we write ES as a sum of EI for OI in S for any subset of S of 1 through N set, then each cone indexed by this compatible pair IF is spanned by these vectors EI when I is for those I inside the independent set, and the minus E complement F for all the flat F in the chain inside the chain is curly F. Yeah. And in this case, the corresponding simplicial complex is the augmented Bergman complex. And also this augmented Chow ring is actually the Stanley-Reisner ring of this augmented Bergman complex, modeling out this linear form. And so now when M is B2, this is an example of an augmented Bergman fan. So these are the rays, one-dimensional rays. They're with their compatible pair, they are spanned by these vectors itself. And you can see now each of these rays, if they span, you just need to check if they span a cone, if that they can be these compatible pair can be put together larger compatible pair. So this is a cone, this is a cone, this is also a cone like this. So this is the augmented Bergman fan, and it's also the normal fan of the stellohedron. And now if we take a sphere intersecting with these things, we get this simplicial complex, the augmented Bergman complex. So this is also the boundary of the dual stellohedron. And now we have a second way to construct a stellohedron. So this is the Postnikov, Reiner, and Williams construction. We consider the Boolean lattice Bn. And in this case, the graphical building set of the N-star graph K1n. So K1n, you can think of it as so this is an example when K is K12. K1n is just you have a star, but you have N branches coming out. And the graphical building set is just a way you can define building set in terms of graph. So in this case, the graphical building set is just a subset of the vertex set such that the induced subgraph on this subset is connected. So in this example, these are the graphical building set. And in this case, the reduced nested set complex, they show is combinatorially equivalent to the boundary of the dual stellohedron. And I didn't say how you construct the reduced nested set complex, but in this case, these are the reduced nested set complex. It's the boundary of the dual stellohedron, so it's also a pentagon. And each of the phases are kind of like corresponding to like a graph like this. We compare this, we show that there is a poset isomorphism between the phase lattice of the augmented Bergman fan of the Boolean matroid and the phase lattice of the reduced nested set complex of these. Yeah, and the bijection kind of just look like this. Yeah, this is each phase corresponding to these cone. And later we found out these can be generalized to any matroid. So to do this, let's first introduce a new construction. So now we have a matroid M that is a flat Ln and In. We will construct the new poset, this L tilde N as the following. So we can just maybe look at an example. So M is a uniform matroid. You can think of it as 3 general vectors inside the plane. And in this case, the lattice of flat of a matroid is this thing. And the independence complex, you consider the inclusion of all the independence set, you get this lattice. And this is actually the phase lattice of the independence complex. And what we did is just we put these two posets like this way, and then we define, so all the relations within these posets are the same, and we define between these posets this cover relation. And how the definition is just for any independent set here, it is covered by the closure of these independent set in the lattice of flat. So it means the smallest flat that contains this independent set. For example, 1, 3, the smallest flats contain 1, 3 is just 1, 2, 3. So we have this cover relation. And then, so we have all these both edges. And this is the new poset we have. And then we take the building set to be this thing. In our example, it's actually all these 1, 2, 3, and then the whole lattice of flats. And in this case, we showed that the phase of then for this building set and this lattice, the phase of the reduced nested set complex are of the form like this, where this I and F forms a compatible pair. And so we can construct the poset isomorphism between the phase lattice of this new reduced nested set complex and the augmented Bergman fan of the matroid, of a matroid M, by just, well, they are just connected by these compatible pair. And we further show that if we consider under this L tilde MNG is algebra DLG, it is exactly equal to the augmented Chow ring. And so, yeah. And this connection was also independently found by Ure and later included in their paper with He and Larson. Okay. Yeah, and so that's why we know that this DL tilde MG is the augmented Chow ring. So we have a basis coming from Fechner-Izinski's theory, and turns out just like this. And that's kind of how we obtain the basis. And so we fill out these kind of table. We show that this augmented Chow ring is actually, we looking at this new lattice and then this new building set, and the reduced nested set complex is the augmented Bergman complex. Yeah, and the remark here is this new lattice is actually also a lattice of flat of a matroid called the free co-extension of our M. Okay. Okay. So that's the basis part of our. Now next we want to switch focus to the combinatorics of the two stories. And so let's first recall Stanley's formula, these things. So we see these things show up several times, but what is this symmetric function? What exactly is this symmetric function? What structure does it have? So Sharashian and Wax, they define some variant of descent set called DEX, and they introduce the Eulerian quasi-symmetric function as defined as the following. So this is this F is Gassow's fundamental quasi-symmetric function, but indexed by DEX, and you sum over permutations with fixed exceedance J, so Q and J. And they show that, okay, if these Q and XTs are summing all up all the J with T to the J, they show that the generating function of these things this has the same formula, closed formula. Yeah. And so this implies that these Q and JX, they are actually, this symmetric function actually equal to the forbidden characteristic of all of these. And so it is a symmetric function, although the sum is fundamental quasi-symmetric function. It is a, yeah. And they also show that the principal specialization of these Q and symmetric function, you'll obtain these Q analog of the Eulerian polynomial, where Q is represented by major and minor exceedance. Yeah, and we denote it as A and QT. And now the combinatorics of binomial Eulerian story. So we recall the binomial Eulerian polynomial and its symmetric function analog. And yeah, A and tilde and Q and tilde. Yeah. So Sharashian and Wax, they also they show that the principal specialization of these Q and tilde gives a very natural Q analog of A and tilde, which is look like this. You just change your binomial coefficient to the Q binomial and AK to this Q analog. And we denote this as A and tilde QT, the Q binomial Eulerian polynomial. And there are a few combinatorial interpretations known for these A and tilde QT, but none of them extend to the symmetric function analog. And also there are no nor involve major and exceedance. Or involve major and exceedance. Yeah. So these are two classical permutation statistics. And so next we consider these decorated permutations defined by Postnikov permutations with two kinds of fixed points. And where we use S and tilde and to denote decorated permutations of length n. But we prefer to think of it as a permutations on the subset of 1 through n set. So for example, these 2, 1, 5 is a decorated permutation. And you can think of it as a permutation on the set 1, 2, and 5. So if you write it out in two-line notation, so 2, 1, 5, you can think of it as 1 map to 2, 2 map to 1, and 5 map to 5. So, and because 3 and 4, there's no 3 and 4, so they are just 0. And then the one line, then we can just take these one-line notation to be 2, 1, 0, 0, 5. This is the one-line notation. And this is the decorated permutation. And you can think of 0 as a second kind of fixed point. And 5 is the normal fixed point. In particular, we define theta to be the permutations on the empty subset, and for any n. So theta, there is one-line notation, is just O0. And when n equal to 2, the decorated permutations of length 2 can be written this way or either in this way. Now, next we show that we can extend these exceedance and major and Sharashian and Wax statistic from permutation to decorated permutations. And furthermore, we have these Q and tilde, it can be expressed using these stacks and exceedance in this way. And now it's counting over decorated permutations. And similarly, for the binomial Eulerian polynomial, Q, this is Q to the major minus exceedance. This has a similar expression as a Q Eulerian polynomial, but now it's over decorated permutations. So we can kind of summarize our combinatorial story. So now let's derangement be the set of Dn be the set of derangement in Sn. We define the following Eulerian polynomial for derangement. So this dnqt, this is counting Q major minus exceedance and exceedance, and dnt is leasting. And we have Q and 0 xt. This is still this sum of this fundamental quasi-symmetric function, but now it's over derangement. Then we will have a following table that illustrate the relations between the combinatorial model, which is right here, and their enumerators, these things lifted to different extensions. And my contributions is So Dn and Sn, these things, they're done by Sharashian and Wax. And my contribution is kind of adding these decorated permutations and interpret all of these in terms of decorated permutations and using these statistics. Okay. So now let's look at the Chow ring and augmented Chow ring of uniform matroid and Q and Q analogs. So this is kind of like a generalization of a Boolean matroid. So uniform matroid, well, we denote as URN when R is the rank. So it's a matroid on 1 through n set with rank R, whose lattice of flats is the truncated Boolean lattice consisting of subset like this. All the so it's subset with cardinality less than R minus 1, and then you join with the top element. And so for an n equal to 3, the lattice of flat of the Boolean U33 is just a Boolean lattice. It's just like this. And that is a flat of U23. For U23, it's just you truncate these lines, so you get this. And U13 is you do one more, you truncate one more, 1, 2, 3, so you just have these. And the Q uniform matroid, we denote as URNQ, is now becomes a matroid on the FQN vector space, FQ to the n. FQ is a finite field of rank R, and whose lattice of flat is the truncated Boolean lattice consisting of subspaces of the FQ to the n space, and the dimension is less than or equal to R minus 1, and then join with the top element FQ to the n, and ordered by the subspace inclusion. So Hamster, Rao, and Simpson, they use the Fechner-Zvinsky for the Q uniform matroid to calculate the Hilbert series. And it's -1 evaluation, and they obtain, well, the Q-Hilbert series have the following expression. So they obtain that it has a combinatorial expression kind of like this. And you can see the first term, this is a and QT, this is a Q-Laurent polynomial, but you need to subtract some term related to fixed point of your permutations when if your rank is R. And in particular, when R is n, there's nothing being subtracted. So this is just a whole Q-Laurent polynomial. And when turns out when R is n minus 1, it's kind of surprising. You will get the derangement type of Laurent polynomial, Q-Laurent polynomial for derangement with this t to the -1. And so in our case, we will start with looking at the representation on the Chow ring of uniform matroid and Q uniform matroid. So recall we have Fechner-Zvinsky basis for the Chow for matroid like this. They are indexed by chance in the lattice of flats with some weight for each of these terms. And when n is uniform or and Q uniform matroid, turns out these bases are also permutation bases for the Chow ring under the action of Sn and the general linear group GL and Q respectively. And they are just acting by just permuting these chain, and A1, A2, they are not affected. So they are, you can kind of think of them as just permuting a chain inside a lattice of inside either inside the Boolean lattice or inside the Q Boolean lattice. So we can observe the following 2 points. First is the Chow ring of uniform matroid is the direct sum of the permutation module permuting these chain, which is isomorphic to the induced representation of the trivial representation on the Young subgroup as nu to the Sn. And similarly, the Chow ring of Q uniform matroid is also the direct sum of these permutation module induced this permutation module of the chain of in the Q Boolean lattice, and is isomorphic to these induced representation from the trivial representation of P mu. P nu, so this P nu is the maximal parabolic subgroup, and then to the general linear group. And further, if we can see that if we for each of these composition nu, the multiplicity of these induced representation in the Chow ring of uniform matroid and the multiplicity of these representation in the Q uniform matroid are the same. And now if we're just looking at this induced representation of Sn, S lambda be the irreducible as a module indexed by this partition of n, then it is well known that this induced representation is decomposed into irreducibles in like these, where this k lambda mu is the Koska number. And Steinberg in 9849, that he showed that for each of these partition of n lambda, there exists a unique irreducible general linear GLNQ representation, which we know as S lambda Q, such that these induced representation, P nu, has a decomposition parallel to these decomposition. And so their multiplicities are the same. Yeah. And these S lambda Q are now referred to as the unipotent representations of GLN. And because of these, we have two results. First is we can define the Q analog of Frobenius characteristic. So this Q Frobenius characteristic map extends the Z algebra generated by the class of unipotent representation to a ring of symmetric functions over Z, and extending this S lambda Q to the Schur function, and this trivial representation to Hn, this complete homogeneous symmetric function. Yeah. And second is when R is such a permutation in this ring, in this representation ring, then the dimension of these R can be obtained by just taking the stable principal specialization of a Q Frobenius series. And so combining with the observation we have before, we have the conclusion that, okay, now the Chow ring of the uniform matroid Frobenius characteristics is actually the same as the Chow ring of a Q uniform matroid. It's for Q Frobenius characteristic. And if we take a principal specialization, then we can obtain the dimension of these Chow ring of Q uniform matroid. And also using the basis of the Fy tilde M, we show that the similar result holds for the augmented cases. And so now we can present our result about the representations on Chow ring and Chow ring of uniform matroid and their Q analog. So we show that so we can consider now the graded Frobenius series of the Chow ring uniform matroid and also the Q Frobenius series of the Chow ring of Q uniform matroid. And we already see that they are the same, and we show that they have these two different expressions. So you can see first one is QJ0 is related to the derangements, and we have the second this is Q and related to the Sn, and then you need to subtract some term related to this R rank R and these fixed points when the rank is R. And when R is N, so you can see because there's nothing being subtracted, this is just Q and XT. And turns out when R is N minus 1, surprisingly, we will just get these Q and 0, the derangement parts, symmetric function. And now if we take stable principal specialization directly, we will recover the second equation, we will recover Hamster, Rao, and Simpson's formula, which is exactly these things. And we also obtain a new formula. And this DJQT is the Q analog for the derangements parts. Q analog for the Eulerian polynomial for the derangements. Yeah. So we can do the same thing for the augmented Chow ring. So the graded, so we show that the graded Frobenius series of augmented Chow ring of uniform matroid and the Q Frobenius series of the Chow ring, augmented Chow ring of Q uniform matroids has two expressions like these, which is just analogous to the Chow non-augmented case. But just the different parts now, this thing, instead of Q0J, this becomes just QJ related to these permutations. And here this becomes Q and tilde related to decorated permutations. And here we also are summing over decorated permutations. And we need to subtract some R related to the rank. And now the fixed point becomes second kind of fixed point. And so when R is n, there's nothing being subtracted. So it turns out these is just the whole Q and tilde xt for decorated permutations. But if R is n minus 1, this turns out to be just Q and xt. This is for the permutation Sn. And we can take a principal specialization. Then we get this Q analog. This is analogous to the Hamster, Rao, and Simpson's result and our new result here. And similarly, when we plug in Rsn, you get these. N minus 1, you get these A and Qt. Just the for Sn and tilde, this is decorated permutation and permutation. And Hamster, Rao, and Simpson, they also compute the -1 evaluation of the Hilbert series for Q uniform matroid, Chowing of Q uniform matroid. And they show that when R is even, this is 0. When R is odd, you got these alternating formula, alternating sum, where this E2KQ is the Q Euler number, and it can be defined as counting over the reverse alternating permutations, which is defined this way. It's number of inversions. And we show that these terms can actually be simplified into an elegant combinatorial interpretation. So it turns out this is just the Q to the inversion, that's alternating sum is just Q to the inversion number over permutations whose descent set is 2, 4, 6 up to R minus 1 when the rank is R. So it started at R minus 1, didn't keep going. And similarly for the augmented case, this turns out you give a kind of the other half of the result. You're counting Q to the inversion, but over permutations with descent set 1, 3, 5 up to R minus 1. And the other part is 0. Yeah. And we further found out that we can actually generalize we show that these results can be generalized to the equivariance setting and for general matroids. So now if that P be a finite graded poset with rank R and the minimal and 0 hat and 1 hat with these minimal and maximal elements and rank function RKP. Now for subset as of R minus 1 through R minus 1 set, we define the rank subactive poset PS to be the element in P whose rank is in S. And then we join the bottom and the top and the bottom elements. Now we show that for any matroid and a loopless matroid M on 1 through N set of rank R, and then we have G is a subgroup of the automorphism group of M, then as a virtual representation, these alternating sum of the Chow for its degree is homogeneous component pieces. These alternating sum is isomorphic. So this is a virtual representation, but it's isomorphic to either 0 or this is a general representation of G on the top reduced homology of the lattice of flat of matroid, and we select these rank 2, 4 to R minus 1 with some sign. And when M is loopless, and in the augmented case, we got the other half. So it's this virtual representation is isomorphic to the top reduced homology of that is of flat. But now we select the rank to be this thing. So this is the G permutation on these homology group. And if we consider just the uniform matroid, so now let M be the uniform matroid, it turns out that these will, so that if we let SHN, this is the skill hook Schur function associated with a set D of 1 through N set, then we show that now the gradient Frobenius series of the Chowing of uniform matroid evaluated at -1. These things you'll just get the skill hook Schur function associated with this set 2, 4 to R minus 1. And for the augmented case, you will get a scale Hsin-Chieh function associated with this 1, 3 to r minus 1 or 0. Yeah. So this is the great equivariant version for QAnon we had before, and we can just take the stable principal specialization of these identities and recover our results for these two Hilbert series. That's all to say. Yeah. So thanks for your attention.